Good morning, everyone. I am Arabindo Tejeshwar. Today, I am going to present my project titled IoT-Based Smart Industry Monitoring System using ThingsBoard. This project focuses on solving one of the key challenges in industrial environments, which is the lack of real-time monitoring and intelligent automation. In many industries, monitoring is still done manually, which leads to inefficiencies and delayed responses. In this project, I have developed a system that continuously collects data from sensors, transmits it to the cloud, and displays it through dashboards, which also enables for an remote control. So overall, this project demonstrates how traditional systems can be transformed into smart and connected systems using IoT. Introduction to IoT in industries. To begin with, the Internet of Things (IoT) refers to a network of physical devices that are embedded with sensors and connected through Internet. These devices can collect and exchange data in real time. In industrial environments, IoT plays a major role in transforming traditional machines into an intelligent systems. Instead of operating independently, machines become interconnected and capable of monitoring themselves. Instead of just connecting devices, IoT actually creates a data driven ecosystem where machines not only communicate but also contribute to the intelligent decision making. Key features of IoT. IoT provides several important features in industries. It enables connectivity between devices and cloud platforms, ensuring continuous data flow. It also allows a real-time monitoring where machine conditions can be observed continuously instead of periodically. Automation reduces manual work and minimizes human errors. And overall efficiency is improved because decisions are based on real-time data. The real power of IoT is not just monitoring, but the ability to convert raw sensor data into actionable insights in real time. Problem statement. In traditional industrial systems, monitoring is mostly done manually. Workers have to inspect machines and record data, which is both time consuming and error prone. There is also no real time visibility, so faults are detected only during scheduled checks. The key issue is not the absence of data, but the delay in accessing and acting on that data, which leads to inefficiencies. These limitations have serious consequences. Machines may fail unexpectedly because issues are not detected early. This leads to unplanned downtime, increased maintenance cost, and reduced productivity. In industries, even a small delay in fault detection can result in large scale operation and financial losses, which makes real time monitoring extremely important. Project objectives. The objective of this project is to develop an IoT based monitoring system that continuously tracks parameters like temperature, humidity, and vibration. It transmits data to the cloud using MQTT protocol, detects errors automatically, and allows remote monitoring and control. This project is not just about monitoring, but about creating a proactive system that prevents failure rather than reacting to them. System overview. The system is designed using a four-layer architecture. Sensors collect data, the microcontroller processes it, the data is transmitted to the cloud, and finally it is visualized on dashboards. This layered architecture ensures separation of concerns which improves system reliability and makes future upgrade easier. System architecture. The system uses MQTT protocol based on publish subscribe model. The Arduino publishes data and the ThingsBoard cloud subscribes to it. This ensures efficient and reliable communication. The use of MQTT ensures loose coupling between devices and cloud. which means both can operate independently without failure propagation. Here we are using sensors which will be collecting data, then we will be transmitting to the Arduino microcontroller where the data are processed. Then these data are passed through Ethernet cable through MQTT protocol and is connected to the ThingsBoard, which is a cloud-based platform. From there, we can able to see the data in the dashboard. Components used. In this project, the system uses Arduino as the controller, DH22 and LM35 for temperature monitoring, a vibration sensor for machine health, push button for machine status, and Ethernet module for communication. These components were selected not just for functionality but also for cost efficiency and scalability, making the system practical for real world application. Sensor description. Each sensor plays a crucial role. For example, DHT22 measures temperature and humidity, where LM35 provides accurate temperature readings, and the vibration sensor detects abnormal machine behavior. Using multiple sensors allows multiple verification of data, which improves system reliability. In DHT22, temperature and humidity are measured, ideal for monitoring ambient conditions that measure machine performance and operate safely. LM35 is an analog temperature sensor which provides a precise analog IC sensor with an output voltage linearly propagation to temperature. Vibration sensor provides machine conditions. It is a piezoelectric sensor that detects mechanical oscillations. Abnormal vibration and patterns indicate bearing wear, imbalance, and misalignment. Early warning signs of machine failure are detected. Push button is used for machine on off condition. MQTT protocol. MQTT protocol is a connection and communication based protocol. It is a lightweight communication protocol designed for IoT systems. It uses minimal bandwidth and ensures efficient data transfer. It is preferred because it ensures reliable message delivery using quality of service QoS level, which, keep, which keeps resources usage low. The Arduino acts as an MQTT client, publishing sensors telemetry to specific topics on ThingsBoard MQTT broker. ThingsBoard subscribes to these topics, ingests the data, and updates the dashboard in real time. This decoupled architecture ensures the device and cloud operates independently yet stays synchronously. Software stack. The system uses Arduino IDE, embedded C, MQTT libraries, and ThingsBoard Cloud. This creates a complete end-to-end pipeline from embedded data acquisition to cloud data-based visualization. Here, the Arduino IDE, the integrated development environment used to compile, write, and upload firmware to the Arduino microcontroller. Here, we use C language for programming the code. ThingsBoard Cloud is an open source IoT platform that receives telemetry via MQTT, stores time series data, and provides configurable dashboard with widgets, alert, device management capabilities. MQTT library, the publisher subscriber client library, handles MQTT connection management, topic publishing, and QoS negotiation between the Arduino and the ThingsBoard broker. Code structure. The code is modular, where each module handles a specific function. This follows good software engineering practices and ensures maintainability and scalability of the system. Working principle. The system collects data, process it, format it into JSON, and transmit it to the cloud. The data is then displayed on the dashboard. This pipeline ensures efficient data flow with minimum latency, which is critical for real-time application. Here we use sensor to collect data, then we store it as a raw readings, then format it into a JSON format, transmit it to ThingsBoard using MQTT protocol, then we visualize the data in ThingsBoard platform. In this project, we have used two nodes such as node 1 called as production line monitor and node 2 for warehouse management. Node 1 monitors temperature, humidity, vibration and machine status in the production line. This node plays a crucial role in predictive maintenance where early signs of failure are detected before breakdown occurs. Node 1 is deployed on factory floor to monitor critical machine parameters. It tracks environmental condition, machine mechanical health, and operational status, enabling early detection of faults before they are tend to become failed. Here we use temperature and humidity sensor which monitors the temperature of the surrounding and as well as the machine. Vibration sensor which detects the abnormal mechanical vibration indicates the wear and misalignment of the machine. Machine status. It is an digital input tracks whether each machine is running ideal or stopped for operational reporting. Error detection. Built-in diagnosis flag sensor fault immediately, triggering LED alerts and logging events. Note 2. Warehouse monitor. Note 2 monitors light, motion, door status and humidity in the warehouse. It combines both environmental monitoring and security features, making it multifunctional. Here we use LDR sensors, door sensors, motion detector, and humidity tracking. LDR sensors detects the ambient light level for automated light control. Door sensor monitor whether the door of the warehouse is opened or closed. Motion detector. It is done using PIR sensors for movement in the warehouse. Humidity tracking ensures storage condition and remain within the safe ranges. Dashboard overview. Here we have three dedicated dashboards created in ThingsBoard Cloud, each tailored to a specific operation domain. Together, they provide a unified view of the entire facility, from production metrics to warehouse, security, and remote control. Three dashboards, two IoT nodes, and one cloud platform. Production dashboard. This system uses ThingsBoard dashboard for visualization. This provides a single source of truth where all system data can be accessed in one place. This production dashboard displays machine data in real time using gauges and graphs. Visualization converts complex data into easily understandable insights, enabling quick and decision making. In production dashboard, we have widgets for temperature and humidity, machine status display, vibration, and time series graph, which continuously updates and gives the data of each machine in Node 1. Warehouse dashboard. The warehouse dashboard shows environmental and security data. This improves overall situation awareness of the facility. The warehouse dashboard also have widgets for LED value display, door status indicator, motion detection alert, humidity graph, which are time series graphs which keeps on continuously monitoring the machine status in warehouse. and updates the data to the ThingsBoard cloud. Control dashboard. These control dashboards allows user to remotely control devices. This introduces bidirectional communication, which is a key requirement for a complete IoT system. In control dashboard, we have a remote on-off switch, a cloud-hosted toggle sends commands back to the node, controlling connected loads such as indicator, LEDs, or relays. This enables automation, example like turning on lights when motion is detected after dark. Commands are delivered over MQTT downlink, allowing full remote activation without physical access to the hardware. LED status indication. The LED indicator shows system status such as communication failure, sensor error, and normal operation. This acts as an edge level diagnostic tool, reducing dependency on cloud access. Each node indicates a tricolor LED that indicates immediately. At a glance, status feedback for field technicians. No laptops or dashboard access is needed to diagnose basic connectivity or sensor health. Red LED is used to indicate that MQTT is disconnected. The node has lost connection due to the cloud broker. Check network credibility, Wi-Fi signals, or broker availability. Yellow LED. It indicates a sensor error. A sensor reads failure or out of range values was detected. The blinking pattern helps distinguish this form of steady state fault. Green LED is used to indicate the normal operation. All sensors are reading correctly and MQTT connection is active. The system is transmitting data as expected. Now let's go to the project. This is the code for node 1 where we have actuator, network, sensor manager, telemetry and RPC. This is the code for node 1 INO, actuator CPP, actuator.h, config.h. This is the access token which is unique for everyone. Network CPP, network.h, sensor manager.cpp, sensor manager.h, telemetry.cpp, telemetry.h, rpc.cpp, rpc.h. For node 2, node 2.ino, sensor manager.cpp, sensor manager.h, actuator.cpp, actuator.h, configuration. Access token for node 2 is also different from node 1. Network.cpp, network.h, telemetry.cpp, telemetry.h, rpc.cpp, rpc.h. Now let's go to the pixim. This is for node 2 where we have LDR sensor for light detection, DHT22 for temperature and humidity monitoring, PIR sensor. Then we have Ethernet W5500, ventilation relay, door switch, LED display that indicates whether we have normal operation or any critical or warnings. This is we use for transmitting and receiving data through cloud. This is for node 2. This is for node 1 connection where we have LM35 for measuring the surface temperature of the machine, DHT22 sensors for measuring humidity and temperature of the surroundings, vibration sensor which measures the vibration of the machine, W5500 is an Ethernet connection, relay status. Then we have LED and LED operations that used to indicate whether the system operates in normal operation or whether it has any critical or warning status. Machine control. Now let's go to the ThingsBoard platform. In devices, we have two devices such as production line and warehouse. In dashboards, we have three dashboards for Node 1, Node 2 and Smart Factory. Smart Factory which connects both the data of Node 1 and Node 2. We have a time series table for detecting temperature, door open, humidity, time series chart for detecting temperature and LM35 temperature. In node 1 we have widgets for temperature, humidity, time series chart, machine status, relay status, switch control which is an RPC, alarms and sensor error. Node 2 we have widgets for warehouse where we have temperature, humidity, LDR sensor, sensor error, door status, is dark, alarms and time series, humidity chart. Now let's check whether the data which we are sending in Pixim is able to display in the cloud. Now let's check with node 1. Now I am increasing the temperature value. The temperature has changed. Humidity 100, temperature 75. Time series chart for temperature and vibration. The data is up and updated continuously. Machine status, relay status. Then we have alarms if we have critical warnings. We have warning for production line test. Then in and it is showing at high temperature as a critical warning. The relay is on and the relay is blinking here, which is an RPC control which we can control from ThingsBoard to Pixim, where we can control machine from ThingsBoard dashboard. Now let's go to node 2. If suppose we are done on this, see we have got warning that the machine is not working. It is a normal, not in a normal operation. Now it has come to a normal operation. Now let's move to node 2, where we have DHT22 sensor for temperature and humidity measurement, PIR sensor, LDI sensor, door switch and ventilation relief. Now let's move to ThingsBoard. Node 2 warehouse. We are getting a switch request. Request timeout. Now we now we don't get the request timeout. Now we can control it using Pixel. I will reduce the LDR value. Door switch on 86%. Thinking the humidity is 10 to 86, temperature 19, door status on, is dark off, sensor error, motion detected off. See, it continuously monitors the humidity of the machine, and we have got warnings in place of warehouse dark, and the data is displayed continuously for temperature, humidity, and door open. Filter off. Here is dark on errors. Now we will try to control using switch control. Switch control on. The ventilation relay is on. If you off the switch in the ThingsBoard, the ventilation relay in Pixim Lab is also off. This is the working of node 1. Node 2. Then we have a dashboard called a Smart Factory Dashboard. Which monitors the data of both node 1 and node 2. Here the temperature and LM35 data is also measured continuously. Warehouse data and production line data. These data are continuously being monitored and it is displayed in dashboard. This is the overall view of my project. Now the advantages of these systems include the system provides real-time monitoring, low cost and remote access and scalability, demonstrate how low-cost hardware can deliver high-impact industrial solutions. And the applications include the system can be used in industrial monitoring, warehouse security, and smart factories. It aligns with principle of Industry 4.0 and smart manufacturing. The four core application areas are industrial monitoring, warehouse security, machine health monitoring, and smart factories. Now we come to the limitation. The system depends on internet connectivity, sensor accuracy, and may vary, and security is basic. Identifying limitation helps in designing more robust and future systems. In this, we have for connecting it with the ThingsBoard dashboard, we need continued and continuous internet so that we can transmit the data from Pixim to the ThingsBoard, or else without internet it is difficult. And the sensor accuracy limitation, that as prototype may be introduced in measurement of drift or reduced precision under extreme environmental condition. We need industrial grade sensors with calibration protocols for production deployment. And for security implementation, the current security level covers the foundational authentication but lacks advanced encryption and role-based access control, and enterprise deployments will require hardened security aligned with OT and IT convergence standards. Future enhancement. This future enhancement improves the include of mobile apps, AI analytics, automation, and security upgrades. With AI, the system can evolve into a predictive and prescriptive analytics. In conclusion, I would like to conclude by saying this project demonstrates a complete IoT monitoring system with real-time data and cloud integration. It shows how traditional systems can be transformed into an intelligent and connected and autonomous system. It is very useful, and this project had helped me how IoT plays a major role in industries, and I have learned a great things in this project. Thank you for your attention.